All right, well, we got another pretty long question, but this one perhaps is more useful for what we see in the world. I don't really know yet, but let's see what happens. In example 11.3, we assume that the velocity and acceleration were instantaneously, at least, collinear. Carry out the same analysis for the case where they are perpendicular. Choose your axes so that V lies along the z-axis and A lies along the x-axis. And that's the case. We have V equal V z hat, A equal A x hat, and the unit vector script R is equal to sine theta cosine phi x plus sine theta sine phi y and plus cosine theta z hat. Typical spherical Cartesian setup there. So check that P is consistent with the Liénard formula. In the Liénard formula with gamma equal 1 over square root of 1 minus beta again, we see that we get the power radiated through the solid angle is going to be this nasty cross product with the U and A. If you recall, U was the C x hat, or C times the script R hat minus V from earlier. I think it was chapter 10 too. Yeah, that was chapter 10. And so the power, once integrated across and all the other fun stuff, is equal to a bunch of constants with the gamma to the 6th power, A squared minus the cross product of V and A over C squared. Well, let's go ahead and doodle this out like they said. We were told put the V on the z-axis, put the A on the x-axis. So we see that somewhere in space we have script R pointing, where we have phi being the azimuthal angle, theta being the polar angle, and so we see that the x hat, y hat, z hat for the script R vector are what are given. Pretty standard there. Now it's up to us just to, start running through the calculations. So starting from the power radiated through the solid angle with beta equal V over C, define the products. Clearly we need to define what U cross A is and what script R dot U to the 5th R. Again, we have a triple product up there in the numerator, so we're going to use back cab. Go figure, that's our hero. We talked about what U was, so now we can just apply everything. If we want to square that triple product, then we're just taking the dot product of all the back cab products. So you see we have script R hat dot with A squared, U dot U gives us U squared. And then we have a bunch of cross terms here, 2 times U dot A, script R dot A, and then script R dot U, where the cross terms are U dot A. That's really the big thing there. And then finally, we just have a plus script R hat dot U squared and A squared. So what is this script R dot U? Well, if we, plug in U, then we have to distribute the script R, so we get C script R hat dotted with script R hat, that cancels to 1, or evaluates to 1. And we have V script R dot Z hat, which if you recall what was given, that dot product yields a cosine theta. So now we factor C out, kind of force factor it. Then we see we have C parentheses 1 minus beta cosine theta. All right, so that's our X or script R dot U. What is A dot U? Well, A is equal to A x hat, so we still have to distribute that dot product to the U. And we see that when we do that, we get sine theta cosine phi from the x hat direction in script R hat. And then Z and X hat are perpendicular, so that dot product evaluates to 0. So we like that. What is U dot U? Well, that becomes messy, and we just get a script R dot Z hat. So we see that we have a C squared plus V squared minus 2CV cosine theta. Nothing too crazy in those dot products. So now we just need to simplify this triple product, which we saw once we distributed everything was easy to do. You see we have an A sine theta cosine theta or cosine phi squared, a C squared plus V squared minus 2CV cosine theta. We put that in red because in the cross term we see another term that's very similar once we plug everything in and distribute, and those red terms will end up canceling, which is cool with us. We like that. Make our life easier. So then what you see after that cancellation in red is that we have an A squared term in every one of these terms. Okay, and then you see here that from the first term and from the second term, we have a sine theta cosine phi, so we can factor that out, and we're left with v squared minus c squared, since we had a c squared in the in the cross term. So we get that there. Nothing too big of a hardship. Then we have c squared minus 1 times 1 minus beta beta cosine theta squared. Again, you can walk all these steps through. No big deal. Just be careful, of course. Yeah, that should take care of everything there. Yeah, because we had to distribute. Yep. Okay, so everything works out well. So here then, we try to simplify again via the fact that we want to factor a c out. So when we do that, we rearrange everything, and then that v squared minus c squared term, we put that c squared to 1, factor negative c squared out. That way we can take the c squared out of the whole big bracket and put everything in terms of beta. So with that, we get a 1 minus beta cosine theta squared minus a 1 minus beta squared term times the sine theta cosine phi squared. So if we plug that triple product in and we plug in the script r dot u, we see that in the denominator, what we get is a 1 minus beta cosine theta to the 5th. And again, that c squared term factors cancels with the c squared. And then we combine I color coordinated it since we had a c to the 5th in the denominator. A factor c squared cancels with the triple product c squared. And we can also turn that c squared into a mu naught epsilon naught. And that cancels with the epsilon naught in the denominator. So that's where we get the red mu naught in the boxed answer, along with a q squared a squared over 16 pi c. And we get something that looks pretty familiar, I would say. But, let's continue. So with this, now we have to find the total power radiated in all directions, meaning we have to now take the integral of this dp d omega through the solid angle, which of course we know the angles are d phi and d theta. We get a 2 pi, of course, from the phi integral once we distribute, but also remember that cosine squared from 0 to 2 pi gives us a pi. And so I color coordinated all the purples together so we're not distranded. And then you see, since we have a pi in both terms in the numerator after the integration, we can factor that and cancel it with a factor in the denominator for the constants. Here it would be wise to make a substitution, i.e. let w equal 1 minus beta cosine theta to get rid of that denominator. And if we solve for beta or solve for cosine theta, we get 1 minus beta 1 minus w over beta. This tells us that sine squared, which is equal to 1 minus cosine squared, is equal to 1 minus, carry this simplification through to get the expression for sine theta. And once we have everything in terms of this, now we can find what the numerator is. So we have 2, and we substitute in the original substitution, so that gives us a w squared. Then we have a 1 minus beta squared. Now we need to plug in what we found for sine squared and try to simplify it down. So, expand everything out that you can, factoring, push it through. You see we get once we distribute everything, including negative signs, you factor down everything possible. What we did was we put a beta squared on the 2w squared term just to have a common denominator come up soon. So with this, we see we get a, more algebra. It's 1 or 2 steps of physics and 1,000 steps of math. Be careful. Here, based on the original substitution, we have dw from the w substitution equals beta sine theta d theta. So if the sine theta d theta gives us dw over beta, evaluate the limits to change it out so we don't have to back substitute. Finally, substitute everything in and tidy up as best you can there. We get a 1 over beta cubed coming out of the integral. So now we can evaluate the integral. Split the setup and evaluate. So, use a integral tool because I am lazy and I'm not typing everything out. We see that we get a factor of beta cubed that cancels and an 8 that reduces at 16 to 2. That 2 power needs to be rewritten as 4 over 2 for the fact that we want to write this whole thing as a cube. upon resubstitution of everything. The reason why is because when we have it as to the 1/2 power, we can put this in terms of gamma. And then we're left with mu naught q squared a squared gamma to the 4th 6 pi over c. That's pretty cool in my opinion. So, yeah, once we do this, now we can ask, is this consistent with the Liénard formula? Well, V cross A is equal to VA x cross, or Z cross X, which gives us a VA y hat. So A squared minus the absolute value of VA over C y hat. Well, if we're just squaring that, then we can just take the unit vector away. And we're left with A squared minus V squared over A squared over C. Factor the A squared out, put that in terms of beta. And we see that we get A squared times 1 over gamma squared. So if that's the case, what we see is that the power is equal to mu naught q squared gamma to the 6th 6 pi c, and then we plug in A squared over gamma squared, and the gammas cancel and reduce to a power of 4. And indeed, they are consistent. That's, actually pretty gnarly. I didn't expect that to happen, but once we just deal with the math of it, the chunkiness of it, you see where these results actually come from and how much more quickly they are to utilize after a bit of setup work. What we see here is that when we graph the intensity, so to speak, with A and V perpendicular like this, we see that we have a large proponent of this going in the direction of the speed, and that's perpendicular, so that's actually pretty cool. I'll have some more words to say about this particular setup in the description, so be on the lookout, and yeah, have a good one.